Okay, we're back. And let's talk again about systems integration. And this time we're going to talk about interfaces. Interfaces represent one of the more common areas of failure. You can see this cord here has failed right at this interface point where it plugs into the phone. This bridge is a little bit more subtle. This is a concrete span right here, and this is a concrete span, and they're tied together at that point, and that's where it failed. That's similar to what we saw with the Florida International University failure, which I talked about in my classes. It failed at a similar interface point. Interfaces are surprisingly complex. My iPhone does a good job of representing that. Here we have this mechanical interface. It has to fit the socket there, but also electrically there are particular pins on here that have to have the voltages and currents on this side that match what the phone needs on that side. Additionally, messages are exchanged between here, which allows me to download my music to my laptop or upload to my laptop. All of those things must work for me to properly interface my iPhone to my laptop. Now here's an example of the PowerShot camera. There are internal interfaces in this part here that connect the peripherals immediately into the camera. And also within the camera, there are interface points, for example, between the circuit board and the motor that moves the mirror up and down. There's also additional interface points externally. For example, the lens has a hood on it, and the barrel of that lens has to mechanically fit to that lens hood. Additionally, over here we have accessories that are similar to my iPhone in terms of mechanical, electrical, and also passing the appropriate messages. Let's get to my old friend, the jet engine here, and let's look at the interface points there. The first one is this diffuser. Its interface to the compressor is such that it must pass air at a required flow rate to that compressor. The compressor must supply air at a required pressure and flow rate and also density to the combustor for proper combustion. The fuel control system must provide proper signals to the combustor in order to increase or decrease fuel as needed to maintain proper combustion. The combustor provides exhaust gases to the turbine, but they have to be at a particular temperature and flow rate for the turbine to function properly. Now, the turbine does two interesting things. It interfaces to the compressor, providing energy in the form of rotational moment and rotational velocity so that the compressor has the power it needs to provide the necessary compression. The turbine also reduces the pressure and temperature of the gases to a level that allows the nozzle to function effectively. The nozzle perhaps performs one of the more important functions of converting that pressure to an acceleration. Remember, F equals ma. That acceleration is what provides the thrust that moves the engine forward. Very important in a jet engine to provide thrust. And then finally, the casing around all of this provides the mechanical interfaces that keep everything together, allow it to resist vibration and the motion of the airplane. And one of the other very important functions, it provides the interface point to the airframe. Very important because you want the engine to stay on the airframe as it's operating. So we mentioned these type of interfaces. So it can be physical, things fitting together. It can be exchange of energy, exchange of mass. It can also be information. Very important in software that the information, the messages are exchanged in such a way that both sides of the interface can understand them. Why do we need to do this? Well, multiple reasons. We need the tolerances to fit, just like in my iPhone. It would be really bad if this didn't fit into the socket here. We need the electrical signals to match so that this side is sending what this side is expecting. Same with the messages. We also have perhaps regulatory requirements. For example, this phone maybe has a certain voltage and current requirement so that it can be considered safe by regulatory agencies. And finally, we need to be able to build these things. So planning is required. This is the most important thing. And I'm going to go back to my engine here for a moment. The reason that this engine works when it's all brought together is not by accident. some people, the systems engineering team, the systems architects, did work right up front, calculations and preliminary drawings primarily, to figure out the interface points between all of these components, and also to figure out what the individual components needed to do for the engine to work together. Then they communicated that information in the form of requirements and constraints to the various subsystems so that they could design their subsystems to perform the required function and have the appropriate interfaces between components. This is really very necessary. So that means that as a team leader, you really need to express very clear interface requirements to your subsystem leads so they know exactly what they need to build at these connection points. Also, large organizations will develop protocols for testing both the subsystems to confirm that they work per their requirements, but also that the interfaces are exchanging energy, messages, mass, etc., at the required rates or at the required levels to meet these requirements. Very important to have regular communication. Communicate, communicate, communicate. Team leads, the more that you can communicate with your subsystem leads, the better. And then the final thing is plan for change. It is inevitable that when you do the systems integration, you're going to find things you did not expect. So plan for that. Build time into your schedule. Be prepared that you will have to change things based upon what you discover. That is the completion of our systems integration lecture. As always, please email me with your questions and comments, and we will see you next time. That's all for now.